that should be good. My apologies for booking a room that did not have a blackboard. So, yeah, a few things I want to go over. First, user-defined literals. Yeah, so it's a literal, so a string literal, character literal, integer literal, or floating point literal, followed by a special suffix, and it's implemented by a specially named function. So one that's built into the standard library. There's a few for time units. So there's a standard library header chrono, which has everything to do with time, and then so if you include that header and have a user namespace directive for a certain namespace, then you're able to do like 15 ns for nanoseconds, or s for seconds. And what that actually works, so what 15s invokes is a function with the signature, I'm just gonna, doesn't matter what the name of the parameter is, that's the signature of the function. So the return type, in this case, I believe it's like std chrono time value or something like that, don't know off the top of my head. So it's a special named function, which is operator with double quotes, and then the suffix. So the couple things we're going to mention here. The suffix for anything that is custom. So this is in the standard library, so it gets exempted, but anything that's custom has to start with an underscore, and cannot have a capital letter at the beginning, because everything in C++, you're not allowed to have any name that starts with an underscore and then a capital letter. That's always reserved. That's just a language rule. The parameter, if you want it to be, if you want to be able to handle an integer literal, you do unsigned long. For a, floating point literal, you do long double. For character literal, it's char, and for a string literal, you do const char pointer, and then a second parameter, so type size t. If you haven't seen size t before, it's a built-in type that's guaranteed to be, it's sort of the natural type for like array indices on whatever platform you're in. It's guaranteed to be an unsigned integer of some size. On 32-bit systems, that's a 32-bit unsigned integer. On a 64-bit system, it's a 64-bit unsigned integer, etc. Let's just say we called all of these that. So then if we did like 5 underscore ABC, what that does is it generates a call to this version of ABC. If we do 5.0, that one. If we do, say like A, that one. And if we do that or any other number of characters, that's a string literal, so it can be empty, it can be multiple characters, calls this one. In this case, it would pass a pointer to this and then 4. So there's a few useful use cases for user-defined literals. One is things like this, where you're indicating units. So oftentimes, so either that will multiply it by some factor, or will incorporate the unit into the type that is returned. So it would have a different type for like nanoseconds versus seconds, and then it would define how you can add, subtract, multiply, and divide across the different types, depending on the library. So one that we often define is one based on both integer and double for, like called underscore DEG for degree. So all the math we do for anything involving angles will be in radians, like for example for our odometry, but we want to be able to specify things in degrees. So we have something that lets us then go like 7 underscore DEG or 90 underscore DEG, and it's just defined as, so what that would look like is double times 180 over pi. That's the built-in constant for pi. Yeah, so this is the function we define, and then that would allow us to do like 90 actually, this would only work for floating points. We'd have to have a separate one to handle integer literals. And it will not implicitly convert in this case because this is a special syntax for literals, so you have to have a separate one for integer literals, but this will allow us to do like 90.0 underscore DEG. And that would generate pi over 2. Right? One quick thing. In cases like this where you're actually just doing like a constant fact or whatever, it doesn't matter. But if you have something like minus 90 DEG, this gets called with the value 90. The minus gets applied to the result of the function call. So it's equivalent to that because because the minus sign is actually, the minus sign is not part of the, let me just a bunch of those so I can scroll down a bit. So the minus sign is not part of the literal, it's an operator that gets applied to the value of the literal, so the literal gets evaluated first and then it applies the unary minus operator to it. And that applies for integer literals as well. That is also especially important if you're not using it to just like apply a factor or do something that's logically like encoding a unit, because there are some other use cases where you may be using it to construct a relatively simple type. So it wouldn't just return a number, it would return some sort of structure, and so then if you wanted to make sense of negative numbers, you have to define a unary minus operator for that struct or class or whatever. Oh, and there's one other built-in in the standard library, which is I for imaginary number. There's built-in support for imaginary numbers in the standard library, so if you include the right header and whatnot, then you'd be able to do like 1 minus 7i, and it would just work, which is nice. Okay, so that's it for user-defined literals. The next topic is mutable fields. So sometimes in a certain class you'll have like a field which you think you should be able to modify even from the context of a const member function. So just a quick review from last session. So we have like some class, let's say for whatever reason we say, okay, even though this is const, x maybe isn't part of the logical like state of the object. It's not, modifying x wouldn't modify what the object means, it's just something that's sort of related to the object that we're keeping track of. Some scenario like that. If you look through our code, you'll find a couple places where I've done something like this. It's something that's very easy to overuse because it's sort of getting around the whole const attribute, but it has some use cases. So so we want to be able to do something like ++ x, right? This will not compile because this is const, so we can't modify a field. There is some way that we already know how to get around this, which is we could make x a piece of dynamic memory and then define a destructor that'll deallocate it, define a copy constructor that'll do a deep copy and actually reallocate, move constructor, etc. And then here we'd increment the value that x points to, and everywhere we just refer to the value that x points to. And this is legal because we're not modifying x, we're modifying the value it points to, which is not part of this object, so const doesn't mean that we can't modify it, right? But that is inefficient, right? We're doing another allocation, we're using more memory, we're using more CPU time to find that memory and so forth. What we really want to be able to do is say, hey compiler, I know that this is part of the class and it's const in this context, but I want to be able to modify it. So how do you do that? That's not what I wanted to do. So how you do that is you say mutable, which means can be modified. And now this is legal.
So is it still constant then, if you can modify it?
So Any other fields, because the thing that made it const is that within this function, this is a const member function, right? So this is not allowed to modify any members. So if we had another int here, this would not be able to modify y. It's just basically so in the context of a const a, x will not be const. In the context of a const a, y will be const. In the context of a non-const a, neither will be const. But saying mutable means applying the const qualification to a does not carry it through to x as well. So the next thing is sort of related, a little constness. So there is a keyword in C++, constexpr. It's written like that. So it is a specifier that you can apply to functions and to variables, which for variables it means that it's basically that variable is no longer a variable, it's a fully compile time constant. So this means, so if I do this, first of all, it also means that x is now const at runtime. So constexpr on a variable implies const on the type of the variable, and it means that this value basically needs to be a compile time constant, because the whole variable can now be treated as a compile time constant. Things you can put there is literals, expressions only involving literals. You can have, like, for example, size of int, which would tell you like the number of bytes in the type int on that particular platform. Anything that's a compile time constant can go there. And like I said, x cannot be modified. For constexpr functions, it means that the function must be able to be evaluated at compile time for some set of input parameters. So for example, I could have a square function which takes an int, returns the square of that int, right? That is a valid constexpr function because it has no side effects. So basically this needs to be a pure function, no side effects. So that means that a call to this function, because it is constexpr, a call to it where every parameter is a compile time constant, that whole expression can be considered a compile time constant, even though it involves invoking this function, because this function is constexpr and therefore it can work. So one example use case where you might want to do this is, and once we eventually get to defining templates, you'll see a lot more use cases for this because templates are entirely resolved at compile time. But one standard library template is array, which is an array of a fixed length. So if I want an array of integers that's 10 long, I can do int 10. I cannot put a variable here. This has to be a compile time constant. However, a compile time constant can involve calls to constexpr functions. So if I had, obviously if it was as simple as squaring a number, I might just put that directly in there, but this constexpr function can have basically anything that can be evaluated compile time. You can have loops, you can have as much stuff in it. You can't have go-tos, but you should pretty well never have go-tos in your code anyway. If you don't know what they are, good. They should not exist. You can have pretty well whatever you want in here. And also note that it's okay if there are certain branches of this code, or of this function, that will invoke things that can't be evaluated compile time. So for example, you could say, I don't know, maybe this isn't supposed to be just a pure square thing, and maybe it's supposed to only handle non-negative numbers. So you could say if although in that case it'd probably be better to make it unsigned type, but for the sake of an example, I can say if x is less than 0, like print an error to the output and then return 0, right? Right? Okay, so this can still be constexpr function because it for anything that's not negative, it'll just go through this code path and it'll work. And so if I put in like square x here, x is not going to be negative because it's the width of a type. Types can't have a negative size, right? So, and moreover, this is known at compile time. This is all evaluated at compile time. So, even if I put, say, square 5, that'll work. This will create an array that's 25 long. If I put -5, I'll get a compile time error because it went to a branch that it can't evaluate at compile time. Does that make sense? Because it can't print out to output at compile time because that's a side effect, and yeah, it can only do basically math and things like that. For the variable, constexpr implies that the return type is const, or that the type of the variable is const, right? So I can't modify x at runtime. I can't modify x at all, actually. For a function, it does not mean that the return type is const. The return type in this case is int. Now, for the return type of a function, there is no difference between it being int and constant, but as I'm about to show you, it doesn't have to be just a primitive type like int. You can have structs there, you can have other things. You're limited in what types you can use in constexpr functions, which kind of makes sense. I mean, you can't have a type representing like an open file if it gets evaluated at compile time. You can't read and write files when this is just supposed to be doing simple math, like for things like calculating the length of arrays that we need, right? But the language gives you quite a bit of leeway in what kind of types you can have. So you can have void, makes sense. Constexpr function can return void. You can have any built-in scalar type, so any built-in integer, floating point, character type. Any array of any of these types that you can have an array of that type. And by the way, this set of types that you can use is called literal types. So you can have any class where, and there's a set of conditions that the class has to meet. It needs to have a trivial destructor, meaning that its destructor does not do anything, including any destructors that it itself needs to invoke. So your class's destructor does not do anything, the destructors of all of its fields don't do anything, base class, like superclass destructor doesn't do anything, etc. It has to have at least one constructor that is marked constexpr. So this constexpr can be applied to functions, it can also be applied to constructors, and it means the same thing for constructors as it does for functions. It means that it can be evaluated at compile time. So you need to have at least one constructor that's marked constexpr. That's not a copy remove constructor, so it needs to be able to actually create a new instance of the object. And all fields and superclasses of this class type need to be literal types as well. So yeah, you can't have something representing like an open file, but if you had, for example, the 2D vector type that we created as an example in a previous session, that you can work with at compile time, which kind of makes sense. That's just a nice abstraction around a pair of floating point numbers. So it doesn't require any side effects or anything. It's just a collection of two numbers that you can work with at compile time. And that includes, as long as you mark them constexpr, all the overloaded operators that you define for that type, and all member functions that you define for that type, etc., if they're marked constexpr, can be used at compile time as well. There's two very similar keywords, consteval, which can only be applied to functions, not to variables, and it means it has to be evaluated compile time, so it's a compile time error if it needs to actually generate any code to evaluate that function. And there's constinit, which can be applied only to variables, which requires that the initializer is figured out at compile time, same as constexpr, but it does not imply that the variable becomes const. So if I write this as constinit, it means that it needs to be initialized at compile time, so this thing on the right needs to be calculated by the compiler and just embedded in the program as a number, but the variable is not const, so I can modify it at runtime. And that can be used, for example, to catch if something on the right becomes more complicated and you say, no, I don't want that evaluated at runtime, like that's offloading too much computation, or you're concerned that maybe the compiler won't optimize out what's on the right, you're not sure if it actually can be figured out at compile time, constinit will basically say, no, this has to be done at compile time or it's a compile time error. There's one more related thing, which is you can apply constexpr to an if statement. So in a, say, non-constexpr function, or even in a constexpr function, doesn't matter, anywhere you can have an if, you can have, say, if constexpr, and then whatever condition you want. That means the condition needs to be a compile time constant, and whatever branch does not get chosen, the compiler just does not care about. It still needs to be syntactically valid because it needs to be able to parse where the if begins and ends, but for example, you can call functions that don't exist, you can whatever, if maybe that function would have existed otherwise if that was defined.